Continuity is a key notion in analysis, and in particular, it's a key notion in complex analysis. Continuity for real functions of a real variable is defined informally as a function is continuous if you can draw it without lifting your pen. But you never use that definition or that informal definition. What instead you use is that you can interchange the order of taking the limit and evaluating the function. So that is, limit as x goes to a of f of x is the same as f evaluated at the limit as x goes to a of x. Limit as x goes to a of x, obviously a, and so a function is continuous if and only if the limit as x goes to a of f of x is actually equal to f at a. This definition works for complex functions of a complex variable as well. We say that f of z is continuous. This is my particular abbreviation for the word continuous, CTS. You'll see it again. F of z is continuous at z equals a if and only if. That's a very common abbreviation for if and only if. F of z is continuous at z equals a if and only if the limit as z goes to a of f of z is the same as f evaluated at the limit as z goes to a of z, which is just f of a. That is, f of z is continuous at z equals a if you can interchange the order of f, evaluating f, and taking the limit. If a function is continuous at all points inside a domain, then we say that the function is continuous on the domain. The technical definition of continuity has to do with kind of an adversarial situation. Your adversary says, oh, you claim that that function is continuous, do you? Okay, well, if it's continuous, then if I give you any small number, s, then you'll be able to give me a guarantee, a tiny number t, such that if you take z closer to a than t, then the value of f is going to be closer to f of a than my number s. So it's typically written for all s bigger than 0. The symbol here means for all. There exists t bigger than 0. That symbol means there exists. This little symbol, like a backwards epsilon, looks like means such that. So for all s bigger than 0, there exists a tiny number t bigger than 0, such that if you choose z within the disk of radius t centered at z equals a, but excluding z equals a itself, then you're guaranteed that f of z minus f of a is going to be smaller than s. That is, the value of f of z is going to be somewhere within the disk centered around f of a of radius s. One important difference between this formulation here, although it looks exactly like the formulation for the real numbers, is the fact that this geometric picture, the disk, goes with this statement here, but if z was just x, then this statement would be about intervals. It would be saying we can approach from the left or we can approach from the right, and both of those two things have to be the same. Here we have an approach from any direction whatsoever, and the limit must be the same no matter what. So we could approach from the right, we could approach from the top, we could spiral around and dodge away and then come around, and it wouldn't matter how we approached A, then the corresponding path winding around must also approach f of A. That is the fundamental notion of continuity.